So my name is Terry McCann. I'm a Microsoft MVP for the data platform. I also run a company called Advancing Analytics. We specialize in a whole load of things: data science, data ops, data engineering, and a whole load of other bits and bobs. Just a quick plug up there for my podcast. I run a podcast called Data Science in Production, and it's all focused around trying to help people take their models from idea into code and then ultimately into production. So this session and a lot of the stuff that I talk about is all very much geared up around this. It's trying to help people really accelerate their models into production. So what I commonly see with people who I try to hire or people who I see in my consultancy work is a lot of the things that they're building are being built and they're sort of living and just dying on a developer's laptop. And they're never making it all the way into production. And then when things don't go into production, it means it's really hard to try and justify the return on investment for a team, which is quite an expensive team to operate with. So that's what we're looking to do. That's what the podcast does, and I have a bee in my bonnet about it. So if anyone has any questions, just shout them out as we go. We've got quite a nice group, so we can have a bit of a conversation around anything you're interested in. OK, so out of interest, hands up, who is a data scientist or aspiring data scientist? OK. Who's a software engineer or more software-y person? OK, good. All right, cool. So what we're looking to do with a lot of this stuff is try and combine these two worlds as much as we can. So take core learnings from software development and core learnings from data science and try and bridge them together to enable us to really accelerate these models into production. OK, so we're going to look at a few things. In this session, we're going to understand what data scientists do well and what we do badly, because a lot of data scientists are so smart and so clever, but we suck at a lot of good engineering things. So we'll have a look at some of this stuff. We'll explore the history of DevOps. We'll look at some of the core components and how they relate to machine learning, because a lot of this stuff is heavily based on software engineering and isn't really catered for a lot of the stuff that we do as data scientists. And then we'll look at how we can hook this all together with a demo of looking at Azure DevOps. We'll do some Python, some Docker, and also some Kubernetes. So we'll do some of it on my laptop. We'll do some of it in Azure. We'll do some of it through Azure DevOps. There's an awful lot, so we'll see how far we get into it. But I'll give you a link to a GitHub repo that steps you through examples of doing all of this stuff that we want to do. All right, so let's look a little bit at the machine learning process. So typically what happens is you'll go out and you'll gather some data, you'll prepare that data, you'll visualize that data, and you'll try and get a really good understanding of what it is you're trying to do. Then you'll select an algorithm, maybe something like you want to predict a numerical value, you'll pick a regression algorithm, maybe you want to do some, understand some patterns in your data, you'll pick something to do with clustering. And then what you'll do is you'll take that, your data and your algorithm, and you'll like squish them together, and that'll tweak a whole load of parameters inside this algorithm and hopefully generalize to the point that you can use it to make predictions on new data it's never seen before. We'll evaluate that model. So we'll say, how good is this model? Does it actually generalize to my business problem, or have I underfit it or overfit it too closely to the data that we're working with? Then we'll probably do some hyperparameter tuning maybe on that. We'll try and get it to the point that it's the best model it can possibly be. And then we'll test it. That's when we get some new data it's never seen before. We pass it through this model, and hopefully we get a prediction. Now, this is what's known as the 7 steps of machine learning. And this was from a Google advocate who works for Google, I can't remember what they actually call themselves. And this very much sort of mirrors a lot of processes. So if you look at things like CRISP-DM, the cross-industry standard for data mining, which is another very commonly used process that discusses what we need to do as a data scientist. And the fundamental thing that all of these seem to miss is this last part, which is deploy whatever you are making into production. And now, production is one of these terms, production doesn't mean when it's in the cloud or on bare metal. I mean, production really means as soon as you start making value from what you're building, then arguably that is production. So let's make that red. Nobody seems to be doing this. Nobody seems to be putting stuff into production. Now, I mean, why is it? And it's not because, data scientists don't really, are stupid people or anything like that. But I think it fundamentally comes down to this. And this is a quote from Sutton O'Neill from Doing Data Science Straight from the Front Line, a book, where they say that the productionization of models is the toughest problem in data science. And now, if you're new to data science, that sounds like, that can't be the toughest problem, surely. The toughest problem is me, building out this multi-layer deep neural network or really trying to understand the data. And yes, those problems are hard. But we can always find people to do those problems. Those people, exist, and there are lots of them. But finding somebody who knows enough about doing that and also enough about software engineering to actually get things into production does make this one of the toughest problems in data science. But why? Why is this the toughest problem in data science? Let's take this small example here, okay? Let's look at the languages that we use in data science. Commonly you'll find people using R, you'll find people using Python, Julia gets used a lot, Scala is used a lot. So if anybody came to my pre-con, we looked at doing machine learning on PySpark, in Spark. You can do machine learning in SQL Server now. You can do it in MATLAB. You can do it in a whole load of different places. And that makes it very difficult. Because what we never want to do is go into a company and say, okay, well, what is it? What do your teams do? And say, well, okay, you're an R developer. We get that. You're really good. We've hired you as an R developer. But, our production language is Python. So forget everything you know about R and start learning Python. That's just going to kill productivity. And if you take on maybe somebody who's come straight out of university and they've looked at something really interesting, maybe Lua or another really interesting language or technique, you don't want them to then say, well, forget all of that stuff, because R's our production language. So we need to work out a way that we can handle and support a multi-language environment, because inevitably that's what we're going to end up with. Okay, so let's introduce some people. Let's introduce my beardy friend here, our data scientist. And typically, the customers that I work with, we often find that data scientists are generally very highly academic, very highly skilled, quite highly educated, lots of master's degrees, lots of PhDs. PhDs, in my opinion, entirely unnecessary. I was talking about this, or maybe on Wednesday. If Google DeepMind don't want you to have a PhD to work for them, you don't need a PhD to work for your local lawyer firm as a data scientist. But they are generally very highly academic, very statistically minded, particularly strong in those machine learning languages that we've just discussed, but generally never coming from a software background. Oh, just spat coffee in my eye. Thinks testing is hard. Testing is hard. Testing's particularly hard on data science. I agree with you, data scientists, but testing is hard. They typically don't use source control. Who's using source control? It's a good amount of hands. All those hands that didn't go up, your number one takeaway from this session is start putting stuff in source control, because source control just helps everything. If we look at the data science process, typically what we do is we get some data, and maybe we spin up something like a Jupyter notebook, we import that data, and then we start iterating over it, picking one model, seeing if that works for us, and maybe we go, that kind of works for us, that gives us an okay accuracy, and we're like, I'm going to try something else. I delete that stuff, and I try something else, and that gives me a bit of a better accuracy. I'm like, cool, I'm doing the right thing here, and I try something else, and I destroy the accuracy, and I'm like, oh, what was that code I just had? I was like, oh, I don't know, I just deleted it because I thought I was making it better. I could have source controlled it and then just go back and get those previous versions. Source control is super important as well for things like accountability, especially if you're in a regulated environment. And our data scientist, he thinks that deployments are the responsibility of someone else. I've had this on interviews where I've said to someone, tell me about a machine learning project that you're really passionate about. And they go on and on and on, and they are clearly passionate about it. And you say, great, how did you deploy that? How did you get that into production? And they're always like, well, that's not my responsibility. That's someone else's. And maybe it is. Maybe it is. But ultimately, the models are not making it into production. They are not being able to return that investment that is being put into that team. So how do we fix this problem? Let's talk a little bit about DevOps. Who's familiar with DevOps? Okay, cool, lots of hands, good. So for anybody who's not familiar, DevOps really came about from a frustration between two areas of a business, which was really your development teams and your operational teams. So let's talk a little bit about my friend here, with my mustachy friend here with his cool sunglasses, who is our developer. So our developer, he writes his code in Python. He writes new features, he fixes old code and bugs, and he waits weeks to deploy his code. So this is one of the main things that really came out of really why DevOps started to appear, which was that the amount of time to go from something that you've built to being deployed is really, really hard. There's a lot of stuff. If you've got a lot of different dependencies that work in there, it becomes very hard to get your stuff deployed, and ultimately it takes a lot of time. You start losing a lot of value. The time to market for our product, because of this, it's suffering. And our customers, they're just not happy. And so this was a very common scenario, and it's still a super common scenario. You know, this happens everywhere. And ultimately, as a developer, it's not my problem that this stuff is happening. It's these operational guys. They're too slow. They just can't work with the stuff that we're building. It's operations. We've got operations over here. And operations are like, I manage production code, but our production code is in Java. So we've got our devs over here writing in Python, but anything going in production is going to have to be rebuilt into Java. He's also got a problem that his environments aren't the same. Dev, test, production, they're not the same. They're different. Maybe one's on the cloud, maybe one's on premise. Things are difficult. He's responsible for a 99.9% uptime. So he has like no window really that he can take things down. He manages hundreds of servers. The company is growing fast, and so is his responsibility. He owns the bugs from deployments, and he thinks that developers just don't care about his uptime. So there's this huge conflict of interest between both sides really thinking that one person is doing the wrong thing, and ultimately it just means that stuff just doesn't really start to happen. So ultimately what happens is you build up this big brick wall between them two, and you just sort of like lug some code over it, and I've done my bit, now you do your bit, and that's just sort of what happens. And as a result, things take a lot of time, things break down. How do we fix that? We bring them together. Come together, my friends. And they come together, hopefully, to form a team of DevOps, which is taking the core skills of developers and the core skills of operations and trying to combine these two together in a multidisciplinary team so that they're working together, they understand what's happening, and ultimately they can just do everything in a very common way. So rather than saying, okay, well, what do I need to get my code into production? Well, you've got operations there from the get-go. Right. So what is DevOps then? So DevOps first and foremost is a culture. So lots of people think, oh, well, DevOps is Azure DevOps. It's a set of tools. Yes, it's a set of tools that facilitate a culture. Without the culture, everything around DevOps will ultimately fail. You need a decent amount of buy-in from the business, from a very high level down, for any of this stuff to ever actually work. Because there's a lot of stuff to set this up. There's a lot of time that's going to be spent that doesn't look initially, like productive time. So you need buy-in. You need culture. You need source control. If you think about this stuff as a pyramid, that bottom tier is source control. None of this stuff works without solid source control. Continuous integration, continuous testing. When I put something into source control, I need that to be tested. I need to ensure that anything I'm building is being tested and is in a state that it can just go straight into production. If it's not, it gets thrown out, errors are raised, somebody fixes it until it's at that point that it is good to go. If it's good to go, hopefully we can get to the point of continuous deployment. Who uses Spotify? Yeah, if anyone uses the Spotify desktop app, you may notice it happens a little bit less frequently now, but about maybe a year ago, you'd have every couple of hours, you'd have a little notification pop up in Spotify saying, Spotify needs to close, so next time you close it because there's been an update, and you'd close it, and then about 3 hours later, it'd pop up again and say that you need to close it to reapply these new updates. And that's because Spotify's continuous deployment routine was down at the sort of level of roughly about 3 to 4 hours. They're shipping code from built to roughly deployment in roughly about 3 to 4 hours. They're able to get this stuff super fast and pushed out. So we do infrastructure as code. And now that's really hard on premises. It's very easy in Azure, and we can have a look at that. We look at configuration as code. So everything that we're trying to build, we're going to code it out. Every configuration we're going to apply to that, we're going to code it out. So now what we can do is we can commit our code for our application alongside the code of what the application is going to run on, alongside the code of how that application is configured. I can take those 3 things and deploy them into my environment. I can take those 3 things and deploy them into someone else's environment. If I need to scale, I can scale that way because I have everything I need to just get this stuff built. And ultimately, we want to apply a heavy amount of automation here. Everything we're doing, we want to try to automate, make it as quick and as easy as possible. Then we move into the operational monitoring and feedback. So we've got lots of dev stuff there, but ultimately, we're working in a multidisciplinary team with our operational people. When things go into production and when these things are automated, we need some assurances. We need to make sure that everybody is happy, so we add this level of operational monitoring and feedback, and we make sure people are happy. Okay, so let's automate the deployment of some data science with DevOps. So what are we going to look to do? We're going to look to do something a bit like this pipeline. So we're going to start down the end there with somebody building out a machine learning model in Python. They'll be doing it maybe on their laptop. And what they're going to look to do is whenever they make a commit of their model in their Python model, we are going to store that code into Git through VSTS, which is Azure DevOps now. And once that's been committed, we are going to build that. We're going to test it. We'll make sure that everything in there actually succeeds. And then we're going to look to containerize that. So we're going to use Docker to package that up into a container so that we've got somewhere that we can run it. We are going to push that Docker image up into a container registry, and then we're going to tell Kubernetes, hey, point at this container registry, this has got my Docker image on it, and just run it. Get that running, get it orchestrated. Okay, so let's talk a little bit about some of these things. So Git's our source control. It's got a remote repository in Azure DevOps, so we don't need to worry about configuring anything there. Docker, I'm going to run Docker on my local laptop. I'm going to use Docker for Windows, but I'm going to use the Linux version, so it uses a Linux machine running on Hyper-V on my laptop. If you install Docker, install on a Windows machine, install Docker for Windows, but don't select Docker for Windows where it runs it on a Windows VM, because it's awful. Just use the Linux one. You don't need to worry about it, and you know it will work. It's Linux. Linux just works. Windows, it's not so much. We're going to use a container registry. So what a container registry is a place that we can pot Docker images. So if we get a Docker image built on our local machine, we're going to need somewhere that we can actually store this. We need somewhere where we can potentially share it with somebody else and ultimately share it with our Kubernetes service. So having a private container registry in Azure through Azure Container Registry is a great way to do that. And then the last one there is our Kubernetes. So Kubernetes is a container orchestration tool. It can orchestrate Docker, it can also orchestrate Rocket. So you've got these 2 different container options that it can use, and it does a whole load of good things for you. So what Kubernetes will do is enable things like automated load balancing, elastic scale. So if we build a machine learning model and we deploy it through this process, and on day 1, we put it live and we have maybe a handful of people use it, there's no real concern there. It works very quickly. And then what happens is we have a few more people use it. The business think, this is actually very good. This is actually providing us and actually generating some business. So maybe let's expand our A/B test. Well, let some more customers see it. And then let some more customers see it until all of our customers are seeing it. And there are millions of requests hitting this service every single day. Now, running under one single Docker image, that's probably going to struggle. But we can scale out as much as we like here. Kubernetes essentially just works on its lowest level is a pod running a container. We can say, well, give me 2 pods, give me 3 pods, give me 4 pods. And this will all sit behind a load balancer. So you don't even need to worry about those requests coming in. You're just saying, here's my IP address, here's my REST API, go away and start working. Okay, so let's have a look at some of this. All right. So I have got a Python model Let's zoom in with this one here. Super basic, right? What it's doing is it's importing. Still quite small. Can I go in a little bit further? This tool is very right. That's probably about the best we're going to do. So we're up the top there. We are importing NumPy and we're importing scikit-learn. From scikit-learn, I'm importing a datasets library. I'm also importing a linear model. So what we're going to do is going to do some linear regression of a diabetes dataset. This diabetes dataset is a very well-used data set. I can't remember who it comes from. If you search for diabetes and machine learning, you'll find it. It is a load of features plus one label. So features and labels, so anybody who doesn't know what I'm saying there, these are terms as data scientists that we use to try and alienate people from our industry. So we change commonly known things to other things so that, there's this barrier so that we make sure that we just keep all the jobs. No, so we have features. Features, you can think of them as just columns in our data, and a label is something that we're trying to predict. So in here, what I'm doing is I'm importing a data set called diabetes. I'm splitting it into my test and train. So very common, I'm going to take my whole data set, put some of it, in this case, 80% to be trained with, 20% to be tested with. That's how I'm going to do that evaluation stage. Then I'm going to import a linear regression model, and I'm going to fit that model with my data, and then I'm going to test it, do some predictions. So I'm basically here instantiating a model. I'm keeping that model in memory. I'm going to pass some requests to that model, pass it a new value, hopefully get a prediction, and then print that out. So I have got a command window running here. Wrong one. Let's go for the Anaconda one. So I'm using the Anaconda distribution on my machine. So Anaconda is a great way to get working with Python. And let's just loop back through a whole load of things that I've done until we get to one that we want. Right, okay, so here what I'm doing is I'm saying in my Anaconda prompt is go and run this Python script. So if I run that Python script, it's going to print me out my prediction there, which you might be able to read, which is 11411, it says, okay? So what I can do here now is head over to this window, change this to something which is a bit more realistic, 1.23, save that guy, run it again, and what we get is a completely different prediction. Now, maybe that's cool. Maybe this is a way that I can work with this. I can have this bit of Python running locally and just pass requests to it, but that's probably not going to work for me that well. So maybe what I want to do is expand this a little bit further. So one of the ways that we can do that is by trying to wrap this stuff up into an API. So taking some of that software development skills, actually looking at our problem and wrapping an API around it, so wrapping a REST API, so that we can now say, well, rather than actually going and running that Python script, I'm going to get that Python script running, but now what I've got is I've got an endpoint that I can just point at. I can pass a request to, and it will give me a response back. So to do that, this code is using Flask. Flask is an open source Python REST service. So very much like, I don't know, ASP.NET or something like that. It works in a very similar kind of way. It spins up essentially a very basic web server running in Python, something that can interpret your request coming in and give you a response back out. So we're using Flask for that. We're using request and JSONify. So I'm going to convert my response back into a bit of JSON and pass that back out. Because what I'm trying to do is build something that can integrate well into other systems. If I integrate with JSON, everybody knows how to work with JSON. Any software developer can then interact with that and get it working. So we've got a couple of core things in here. I'm starting a Flask app, and I'm giving it a root. I'm actually giving it 2 roots. And this isn't probably what you'd want to do actually in production, but for this, and with this small example, it works for me. So those 2 roots are training and the scoring. So what I'm doing with this model is once it's deployed, what I can do is I can go to that REST API, and I can write, it runs on localhost /train. And every time I do that, it's going to retrain my model. So if I have this pointing at some external data, maybe on a file system or up in Blob, and that data is changing, in here I can just go API /score and get, /train and get this to retrain every single time. And then once I'm happy with that, I can then come down and just call my /score. So you'll see we've got train here, which contains all of that code that we saw before, but it's doing one extra thing. It's opening a pickled version of my model. And so what pickle is a library in package which will serialize an object for you so that you can use it again. And so what we saw in that first script was, if I wanted to get that response, if I wanted to get an answer back from my model, I'd have to run that entire thing. And that would give me it. So that's that whole entire train process just to give me that one answer. And we definitely don't want to do that. These models may take a couple of minutes to train, they may take a couple of hours to train, they may take days to train. So a customer I'm working with at the moment have a deep neural network which uses ResNet 50 that looks at aerial images. And that model takes roughly about 3 days to train. So I don't want to wait 3 days just to get a response. So I need some way to train my model and then take that core object of my model, save it somewhere else that I can then take back and import somewhere else and pass some scores to. And that separation gives you a whole load of flexibility in what you're doing. It means that, yeah, you could do your training here, and then you're scoring somewhere else. So in the pre-con, we were looking at Azure Databricks, which is a scaled out way of processing your data, so over a cluster. And over a cluster, training a model can give you some benefits because you scale out your data and each one is doing a small amount of work and then ultimately bringing it back together, and then you take that model and you put it somewhere else. So pickling is a good way to do that. There are serialization objects in R, in Scala, in anything you want to do, there's some way that you can do this. Okay, so let's get this one running. And where am I? Here, and it's called Flask. Okay, so what you might be able to see there is Flask has now spun up an API, spun up a web server with debug on, and it said, I've spun this up on your local host running under port 5071. I've said in here, run on port 5071. That port is just any port you want. I think I just hammed it when I wrote this a while ago. So now what we can do is we can go over to our local host. And we can go to our local host. It says not found because I don't have a point here. So this is going into my API, and it's saying, right, I've got 2 points that you can go to. You can go to train or you can go to score. And so what I want to do first thing is I want to train that. So that training is going to run that initial process, and then it's going to pickle the model, and it's going to store that model somewhere on my local machine. So let's run train. And it says, your model has been retrained. Run score to score your model. Cool, thanks. So now if we do score, so this is doing a GET request. So this is a REST API accepting a GET request. You could do a POST request, which is where you package up your response as a JSON object, and you pass that off using a tool such as Postman or something else, and that works also very well. You could just do it like this. It's maybe slightly less easy to work with, but it makes it easier for demo purposes. So here what I've done is I've gone localhost on port 5071, run my score, and return me whatever the var1 is. So var1, if I change var1, let's switch that over to, let's change that one to 2. Oh, not to the number 2, that's not very helpful. There we go. Change that to 2. We get a slightly different response. Change that to 0.123. And we get that response that we saw before. So now I can use this if I want to and get that working. And that kind of works for me. But with any machine learning project, one of the hardest things to handle is deep dependencies in our code. So let's go back and let's have a quick look at the dependencies that we have for just this model. So in Python, in this particular model, we have got Flask. We've got Flask RESTful, we have Pickle, we have NumPy, and we have scikit-learn. So we've got these 5 libraries that I need to be able to just run this one model. And now this version of Flask is running on something like 0.12.2. Flask RESTful is running on something, Pickle's running on a particular version, NumPy's running on a version, and so is scikit-learn. And now, this stuff changes very, very frequently. And so as a developer, I might write this out and just write it like this, and then pass that off to somebody else. And maybe our production system that this is going to run on, our production server, well, that's actually running an older version of scikit-learn that doesn't have the particular data set that I need, or doesn't have that particular model that I need. And then when that goes to be deployed, it's going to fail. So we've got a dependency problem. And managing dependencies in any language is typically quite hard. So we need some way to make this that little bit easier to work with. Right, so how can we do that? We could use Docker. Yes, we could. We could use Docker. OK, so let's have a look at how we might try and do something like this in Docker. Let me just kill that one from running. Because Flask is a nice API, you can see there a history of all the things that I did against it, and it keeps that in a log that you can query, because debug is switched on. To kill that, I can do Control-C, and that will kill that because it's Python. That will just quit that session and stop that from running. If I hop back over here and I try to run my score again, what you'll see is this will just fail. Yep. So it's no longer running anymore. That model is no longer available. Right. So what we could look to do is we could look to containerize this now with Docker. So over in VS Code, I've got a couple of things. I've got this directory here, Docker, and in that Docker one, there's this guy. Oh, wrong way around. Sometimes I can use this tool. My diabetes production Docker. And what you can see in there is a couple of things. So we've got there a diabetes model flask.py. This is my application. This is what I want to run inside a container. I've got my Docker file. Now, a Docker file is what tells Docker what it needs to do. So who's used Docker before? OK, cool. OK, so anyone who hasn't used Docker before, what Docker does is it typically inherits from a base image. And that base image may be something like a version of Python that somebody has built already and published to another container registry, a public container registry. You can have a look at that and go, this roughly does what I need. It's got Python 3.6. It's a particular version of Python that I want. I'm going to use that one. That's going to be my base image that I'm going to inherit from. And then I'm going to apply a load of stuff on top of it to get it to the point that it mirrors the environment that I have. And so that Docker file is going to do that for you. We have a README, which just tells you about it, which you don't really need. We have our regression.pickle. So that is our pickled version of our regression model. And we have this requirements.txt. And what this requirements.txt is doing is telling my model which version you need to actually be using. So each one of these should have an equal number, which says when you build this out, inherit from that base image. But what I want you to do is I want you to install each of these down to this particular version. And that's what it will do. So those ones should all have something like equals 1.2.1 or something. But they don't. So have a look at our Docker file. Docker file is super simple. I'm saying from Python 3, and I'm using a -on-build image. And again, this is not what you would want to do actually in production, because what that -on-build image is, it says, go and get me the latest, greatest version of Python. And we probably don't want to get the latest, greatest version. We want to get the version that we built our model originally with. So we can say in here, use which particular version you want. Then I'm going to say copy over everything from the directory that you're running on and load that into user, src, and app. And that's where my stuff is going to look. So that's going to be moving all my stuff into that Linux machine that's running on that Docker image. And then I'm going to say, well, how should you run? What's your point of interface? And that's going to be running a Python window and running my diabetes model and Flask. So then that knows my Docker image to spin up that API and enable me to start pushing my request to it. So just a brief note on that on-build image. That on-build image is a particularly good one, which looks to loop over a requirements.txt file and then just do a pip install of everything. So it goes, pandas, pip install pandas, pip install this, pip install this, pip install this, and it goes. One thing to note about using these Python 3 on build images is they're very large. If we try to run this one, what it has to do first is pull down, I think it's roughly about a 600 meg image. And that is huge. That has got an awful lot on there. And again, if you're loading this in Kubernetes, if Kubernetes is your endpoint for this service, every time you want to scale that, each one of those needs to go and pull down that 600 meg image every single time. So what you may want to do is lose a little bit of time from actually having something that's pre-built and start off with a very, very small base image and then install the version of Python you want and then install all the libraries you want. And that can go from a 600 meg massive image down to something roughly about a 40 meg, which means if you need to scale fast in Kubernetes, you can scale fast. Right, so let's get this Docker image running. So as I say, I have Docker running locally on this machine. Where you can see it roughly down here. We have Docker and a whole load of stuff. So I'm just running base Docker. Right. So I have navigated. No, I have not. Which one has got the navigated window? None of you. This one? Are you in the right place? You're not in the right place either. Let's go to the right place. Okay. So I'm just changing directories. Let's zoom in so you can see. I grab my list of things we need to do. Okay, we're going to go to you. Right, so what I've done is I've told my window here to point to the location of my image. So this is, it's gone right to that location where I have my Docker file, I have my requirements, I had everything else. And I've said Docker build -t. So that's saying I want you to build what you see here. Give it a name. It's going to build me an image called production diabetes. And I'm putting that little dot at the end. That little dot's important. It's saying just look at everything in here. This is what you want. And then what it's going to do is going to do a couple of things there. So it's saying step 1. From Python 3 on build, do this stuff. Then it goes down, it says, well, this is what I'm going to run. And then because I've run this already, it's cached, it's very quick. If I hadn't had run this already, it would take a couple of minutes to run and get this all working. So it's not going to work for us. So next thing that we want to do is actually get this running. So now that I have built that image should be running on my local machine. If we run Docker, wrong one, Docker images. So right down at the bottom of our screen there, we can see production diabetes, a few other things, hello world, and a base Python image that we have there as well. So that production diabetes is there, ready. We can actually get it running. All right, let's run that now. So let's run that as a container on this machine. Let's get one I did earlier, which has got the right syntax. Not in that window. Not in that window. Okay. Cool. I am just going to grab the right syntax. So anybody who wants to ever step through this stuff and do it yourself, you can by all means go to my GitHub, and there's a huge repository called Machine Learning from Model to Production using the Cloud Containers and DevOps. I'll have a plug for this. This is actually a full-day training session that I run. I'm running it in Data and Devon in a couple of weeks. But you can go here, and it has a whole load of labs. And one of those labs is actually running our model in Docker. And the reason I need this is because there's just a little bit of port forwarding logic, which I always forget how to write. So let's go and just grab that from here. That looks a bit like this. And let's go back over here. So what I'm doing is I'm saying Docker run and the name of my image. And then what I'm having to do now is if I just said Docker run and the name of my image, it would run that, but my API just wouldn't work. If I tried to go localhost port 5071, it's just going to return an error every single time. And that's because the Flask is now running on the local version of Docker, which is running inside that Linux container running on Hyper-V on my laptop. And so that's running on port 571, but my machine doesn't know to talk to that on port 571. It has no idea what's happening there. So what I need to do is I need to make a port tunnel from my Docker image to my laptop so that this stuff works. Okay, that's given us a little ID, and hopefully, if we go back over to localhost, and we run train, we have our model has been retrained. So now that's our model running inside Docker on a Docker machine. It's not running on, well, it's running on my laptop, but it's running on a laptop running a Linux VM using Docker. Same way as before, we can run score and get a response. Or not, get an error. Either way. Your model has been trained. Cool. Right, okay, that's an interesting error, and that's actually a dependency error that I have injected into my code, let's say on purpose, not by mistake. And so that's actually coming from, did I not specify, I don't think I specified the right version of scikit-learn. Okay, so that's how you can very quickly know. See, look, right? So you can't see, that's so small. So up here, I've just said scikit-learn. And that scikit-learn that I actually need is a very particular version of scikit-learn. And the version of scikit-learn it's just used to build this is just too new for my problem. And now what I'm doing is it's operating in a slightly different way using NumPy, and it's failing. So what I'd need to do to fix that, which I don't have time to now, is come back in here, change this guy to be equal to my actual version that I need, and then it will run for us. And we have to just rebuild that stuff. Cool. So hopefully then what we would need to do next is take our Docker image which is running on our laptop and get that deployed into a container registry. So I have got spun up in Azure. I have got this session data science DevOps, and in there I've got two things. I have my container registry and I have my Kubernetes service. So my container registry is where I'm going to push my image to. What I would need to do here is I just need to do a couple of things to boilerplate my Docker image so it knows where to go. So what I would do is I would first tag it, and just for time, let's have a look at what that syntax would look like. It's this guy here. So here what I need to do is I need to tag it with something. So it's running on my local machine. I'm saying Docker tag my image, tag it with the place it's going to go to. It's going to go to this data science DevOps container registry, and I'm saying give it a version 1. So what I can do is every time I rebuild this, I can increment the version, and I've got a huge history of different versions of my image. If somebody audits me and says, hey, somebody, you built a model that said whether or not someone could have a loan. 6 months ago, somebody was refused a loan. That caused a whole load of problems. We're now trying to sue you. We need to know what you did inside that image that you had live 6 months ago. And if you were just like dropping things all the time, you'd be like, I don't know, I have no idea. But here we get a nice history of stuff. We can log in using the Azure CLI. So the Azure CLI is a nice interface from my laptop to Azure, which enables me to do things like push my image in an authenticated way. And so I'd push that image up, running as Docker push data science with my version 1. And what that will do is poke an image into this container registry. If we look in our repositories, we've got our production diabetes, and we have our version 1 of our image there, this guy here. Cool. So next thing we would need to do is get that deployed into Kubernetes. And for time, what we'll do is we'll look at how we can do that in DevOps. So who's used Azure DevOps? Cool. Good, lots of people. So anyone, again, very briefly, who hasn't, Azure DevOps is a great tool, gives you a whole load of things, gives you boards, so you can do things like Agile Scrum, you can manage your entire workload, gives you a remote version of Git, very much like Bitbucket does through the Jira tools. It gives you repos, continuous integration, continuous deployment, gives you a whole load of great stuff. We are going to use it for continuous deployment. So I have built a pipeline, which looks a little bit like this. Let's go to pipelines, builds, this guy, and let's go and edit here. Edit our pipeline. And my pipeline just does a very simple couple of things. it will go away and it will look for that location on my Git where I've got that Docker file, and the first thing it will do is it will build that image. So do all of those steps that we were trying to do. It will then do the tagging, and it will do that pushing to our repository, and then it's going to say, hey, Kubernetes, what I want you to do is delete anything you have already and then run with this version. We could also do a Kubernetes apply, which just does a differential apply between what we had before and what we have now and does a bit of an upsert. If we go back, we can have a look at a previous run. So the way that DevOps works is it's using a remote repository, and that remote repository is, oh, that's very helpful. That remote repository is a virtual machine just floating around somewhere in Azure, and we're saying, I've got my code, I want you to run on it. It latches onto this virtual machine, it downloads all your code to it, does all your builds, publishes your stuff to Azure, and then trashes all your code. Next time you run it, it does a very similar thing. You can, if you want, ensure that that works in a slightly different way by having it backed up to your own machine. So here we can see, great, doesn't work in it. I think it will just keeps closing my window. Okay, so I can't zoom in, but what you might be able to see is here I'm pushing an image, here I'm running my Kubernetes delete, here I'm running my Kubernetes build. So Kubernetes for code-wise, if somebody wants to go and download that and get this stuff running, Kubernetes works by using YAML. The YAML looks an awful lot like this, and it's just basically saying, look, here's where you need to go. This is where you need to find the image you're going to run. Run that image, and then run it in this particular way. So run it using a load balancer, running it on port 80. The container port's running on 5071, and I am saying, just give me one replica. I could say here, give me 100 replicas, and that would give us 100 replicas. Cool. That build did succeed. I ran it a while ago, and that actually would have got stuff running in Kubernetes. For time, we are almost up. Cool. Okay. So I don't have that image actually running to show you the end result, unfortunately. But what I would say is, for anybody who is interested in any of the topics that we have discussed today, is go and check out I've got like a blog series on all of this stuff, which talks about how to do things like source controlling for your machine learning, how to do source controlling for lots of data science key elements. So how do you source control a Jupyter notebook? Because Jupyter notebooks are notoriously difficult to source control. And I go through that sort of stuff there. Then moving on to how do you set up a pipeline, how do you do other things. But then also a lot of reading around this. So it's basically a copy of my master's thesis, but made a little bit less academic and a bit more interactive. Right. So DevOps will make your life easier. Now, that's just an easy throwaway statement, but it will. If you get this stuff right, it's hard to get right, but when you get it right, your return on investment will just increase massively. People will be happier. You'll be able to get stuff into production faster. There's a survey run by, I think it's run by Puppet every single year, and they ask a whole lot of questions about DevOps. One of the questions is, has your job satisfaction increased since you started doing DevOps? And it does. It massively increases when you can just take away a whole load of responsibility and put it on a system. You can get things running a lot better. So start learning how to get your models into production, automate everything, reduce your time to production, test, code, monitor, manage your models in production. You can find out stuff about me if you're interested. I'm on Twitter @SQLShark. There's stuff about the company. I'm sure I have cards with me as well. Thank you very much. Final plug for the session, Data in Devon. It's in Exeter, which is lovely. And also, you will have feedback forms. Please fill out the feedback forms. It helps the organizers. It helps me. If you didn't like the session, please be honest. If you did like the session, please also be honest. All feedback is great. Thank you very much. Enjoy the rest of your SQLBits. Have a good day.